Mars appears quiet, yet its atmosphere is constantly in motion. With air less than 1% as dense as Earth's, Mars cannot retain heat. Daytime warmth escapes rapidly, and temperatures plunge after sunset. Carbon dioxide dominates this thin atmosphere, freezing onto the polar caps each winter, then returning to the air in spring, driving planet-wide pressure changes. Sunlight lifts fine dust from the surface, sometimes triggering storms large enough to engulf the entire planet. High above, solar wind strips atmospheric particles into space, slowly eroding what remains of Mars' protective envelope. To understand how Mars changed from a wetter world to the cold desert we see today, we must first understand its climate, its weather, and the fragile atmosphere that still shapes it. Mars' atmosphere is extremely thin, less than 1% the density of Earth's, and composed primarily of carbon dioxide, with smaller amounts of nitrogen, argon, and trace gases that help scientists trace atmospheric processes over time. This thin air provides almost no shielding from harmful radiation and allows heat to escape rapidly, causing surface temperatures to swing by more than 100 degrees between day and night. Despite these limitations, the Martian atmosphere remains surprisingly active. Seasonal winds sweep across the planet, sculpting dunes, lifting dust, and creating haze that can linger for days. Wispy water ice clouds drift over the great volcanoes, while in winter, carbon dioxide freezes directly out of the air to build immense seasonal polar caps. These changes reveal an atmosphere that, although delicate, still interacts constantly with the surface. By studying its chemistry, circulation patterns, and seasonal cycles, scientists can piece together how Mars evolved from a thicker, warmer atmosphere in the distant past to the cold, tenuous envelope we see today. Global dust storms on Mars are among the most powerful and dramatic weather events in the entire solar system. Roughly every few Martian years, small local storms begin to grow, feeding on sunlight and rising warm air until they expand and merge into a single planet-encircling system. These storms lift billions of tons of fine powdery dust high into the atmosphere, particles so tiny that they can remain suspended for weeks. As the dust spreads, daylight dims, the sky turns a deep orange and surface temperatures drop sharply while the upper atmosphere heats dramatically, redistributing energy across the planet. During these events, familiar surface features, impact craters, canyon systems, and even massive volcanoes, fade from view beneath a swirling, opaque veil of dust. Spacecraft observations show how these storms reshape atmospheric circulation, drive global winds, and influence long-term climate patterns. They may even accelerate the slow loss of atmospheric gases into space. The sheer scale and intensity of global dust storms reveal that despite its thin air, Mars is still a world driven by powerful, ever-changing forces. Local dust devils are some of the most dynamic weather phenomena on Mars, forming when sunlight heats the surface and causes warm air to rise rapidly through pockets of cooler air above it. This temperature contrast creates spinning columns of wind that can stretch hundreds of meters high. Though smaller than the massive dust storms that sweep the planet, dust devils play an important role in the Martian environment. They lift fine particles into the atmosphere, shaping dune fields and contributing to the planet's persistent haze. Their paths leave behind dark streaks where surface dust has been removed, providing scientists with a natural record of their movement. Remarkably, these vortices have even helped clean the solar panels of rovers like Spirit and Opportunity, extending their missions far beyond expectations. Studying Martian dust devils helps researchers understand boundary layer weather, surface heating, and the delicate interactions between Mars' thin atmosphere and its dusty landscape. Each Martian dawn brings a transformation across the landscape as delicate layers of frost begin to glow in the first light of day. Unlike Earth, much of this frost is made not of water ice, but of carbon dioxide that has frozen out of the thin atmosphere during the frigid Martian night. Temperatures often fall low enough for CO2 to condense directly onto rocks, dunes, and dust, forming bright, reflective patches that blanket the ground for only a few hours. As the sun rises higher, this frost sublimates, turning straight from solid to gas, sending faint wisps of vapor drifting into the cold morning air. High-resolution images show how this daily cycle etches patterns into the soil, subtly reshaping slopes and revealing fine textures on the surface. In some regions, repeating frost cycles create alternating light and dark bands that mark seasonal changes, almost like natural climate signatures. These fleeting frosts offer scientists valuable insights into heat flow, day-night temperature swings, and how Mars' unique atmospheric chemistry interacts with its diverse terrain, revealing a planet still active in subtle but measurable ways. Nighttime on Mars transforms the planet into one of the coldest environments in the solar system. Because the atmosphere is less than 1% the thickness of Earth's, it cannot trap the heat absorbed during the day. As the sun sets, warmth escapes rapidly into space, and temperatures can plunge below -100 degrees Celsius, even in regions that were comfortable by Martian standards only hours earlier. The ground cools first, radiating heat outward, while the thin air above it loses energy almost instantly, creating steep temperature gradients across the landscape. Thermal instruments aboard orbiters reveal this transition vividly. The surface shifts from warm oranges and reds into deep blues and purples as each type of terrain cools at a different rate. Rocky outcrops, sandy plains, and patches of buried ice all radiate heat differently, producing a mosaic of nighttime temperatures. In some areas, frost forms overnight and then vanishes with the return of morning light. Understanding these extreme daily cycles helps engineers design equipment that can survive the cold and gives scientists insight into heat flow, atmospheric behavior, and how dramatically conditions on Mars can change from day. Mars undergoes one of the most dramatic seasonal transformations in the solar system as its polar caps grow and shrink each year. Unlike Earth, where the poles are dominated by water ice, Mars' seasonal caps are made largely of carbon dioxide that freezes directly out of the atmosphere during the long, frigid winter months. As temperatures plunge below -120 degrees Celsius, CO2 gas turns into frost and solid ice, expanding the polar caps until they stretch for hundreds of kilometers across the Martian surface. With the return of sunlight in spring and summer, this frozen carbon dioxide begins to sublimate, turning straight from solid to gas, and re-enters the atmosphere, causing the caps to retreat just as quickly as they formed. Orbiters have captured this cycle in striking detail, showing bright winter frost spreading over dunes, crater walls, and plains before disappearing again with the change of season. The waxing and waning of these carbon dioxide caps not only reshape the landscape temporarily but also drive powerful atmospheric currents, influencing winds, pressure patterns, and the overall climate system of Mars. Water ice clouds on Mars form some of the planet's most delicate and beautiful atmospheric features. Unlike Earth's thick, moisture-rich clouds, these Martian clouds are made from tiny crystals of frozen water suspended in an atmosphere far too thin to hold much vapor. They often appear at high altitudes, drifting across the sky in bright, wispy formations. One of the most striking examples occurs above Mars' giant volcanoes, where moist air is forced upward along towering slopes. As it rises, the air cools rapidly, allowing water vapor to condense into long, feather-like plumes that can stretch for hundreds of kilometers. These clouds change shape throughout the day, lengthening in the morning, dispersing by afternoon, and sometimes reforming in the evening as temperatures fall. Observations from orbit show these clouds tracking seasonal patterns, becoming most prominent when sunlight warms buried ice and releases small amounts of moisture into the atmosphere. By studying their altitude, movement, and composition, scientists gain insight into the daily weather cycle on Mars, the properties of its thin air, and the subtle processes that still transport water across the planet's sky. One of the most important discoveries about Mars is that it is slowly losing its atmosphere to space. Because the planet lacks a global magnetic field, the upper atmosphere stands exposed to the solar wind, a constant stream of charged particles flowing outward from the sun. When these energetic particles collide with atoms high above Mars, they can knock them loose, sending oxygen, carbon, and hydrogen drifting into space. This process, known as atmospheric escape, has been occurring for billions of years and is one of the primary reasons Mars transformed from a once warmer, wetter world into the cold desert we see today. NASA's MAVEN mission has measured this loss directly, watching as solar storms intensify the stripping effect, sometimes increasing escape rates by a factor of 10. MAVEN's observations reveal how different gases leave the planet, how solar radiation breaks apart molecules, and how Mars' thin atmosphere continues to evolve. By understanding atmospheric escape, scientists can reconstruct the planet's ancient climate and learn how long liquid water may have persisted on its surface. key clues in the search for past habitability. Martian sunsets are among the most striking sights in the solar system, bathing the horizon in a cool blue glow rather than the warm reds we see on Earth. This unusual color comes from the fine, powdery dust suspended in Mars' thin atmosphere. These dust grains are just the right size to scatter red light outward, away from the direction of the sun, while allowing blue light to pass more directly through the haze. As the sun sinks below the horizon, its rays travel through a longer path of dusty air, enhancing this selective scattering and causing the sky around the sun to turn a deep, almost icy blue. Because the atmosphere is so thin, the transition from daylight to twilight is rapid, and the glowing blue halo appears only briefly before fading into darkness. Rovers on the surface have captured these moments, showing delicate wisps of dust illuminated by the last traces of sunlight. Subtle changes in the shade and intensity of the blue glow reveal variations in dust concentration and particle size. By studying Martian sunsets, scientists gain valuable insight into atmospheric structure, dust dynamics, and how even a tenuous atmosphere can dramatically shape the way light behaves on another world. Seasonal dust waves are one of the defining features of Martian weather, sweeping across vast plains as sunlight warms the surface and stirs the thin atmosphere into motion. During the warmer seasons, the upper layers of dust loosen from the ground and become easily lifted by winds that develop as temperature differences grow between day and night. These pulses of activity can begin as small, localized gusts but quickly expand into rolling fronts that travel for hundreds of kilometers, carrying fine particles high above the surface. Time-lapse images from orbit show these dust waves brightening and dimming as they move, revealing shifting patterns of airborne sediment shaped by Mars' rapidly changing winds and low atmospheric density. As the waves pass, they can temporarily obscure craters, dunes and valleys beneath a soft, drifting haze. Seasonal dust activity plays a crucial role in controlling the planet's energy balance, reflecting sunlight back into space while simultaneously warming the atmosphere by absorbing heat. Over time, these processes influence wind circulation, surface erosion, and the evolution of larger storms. By studying how dust waves form, migrate, and fade, scientists gain critical insight into Martian climate dynamics and the mechanisms that sometimes escalate local disturbances into planet-wide dust events. Carbon dioxide snowfall is one of the most unusual weather phenomena on Mars, occurring only near the poles during the coldest periods of winter. As temperatures plunge below -125°C, carbon dioxide in the atmosphere freezes directly into tiny ice crystals, forming clouds that release faint, whisper-like snow. Unlike water snow on Earth, CO2 snowflakes are extremely small, often no larger than dust particles, and fall slowly through the thin Martian air, creating a soft shimmer rather than a visible shower. The polar night, illuminated only by starlight and faint atmospheric glow, is when this snowfall is most active. Orbiters equipped with infrared instruments have detected these CO2 clouds from above, while landers have recorded temperature drops consistent with surface frost accumulating overnight. The seasonal buildup of CO2 snow contributes to the growth of Mars' winter polar caps and plays an important role in controlling atmospheric pressure. When spring arrives, this frozen carbon dioxide sublimates rapidly, re-entering the atmosphere and driving strong winds and regional weather shifts. Studying CO2 snowfall helps scientists understand the planet's extreme climate cycles and the delicate balance between atmosphere, ice, and temperature. The InSight lander provided one of the most detailed views ever recorded of daily Martian weather, using a suite of highly sensitive instruments designed to measure wind, atmospheric pressure, temperature, and even subtle ground vibrations. Positioned in Elysium Planitia, a region selected for its relatively smooth and stable surface, InSight continuously monitored how Mars' thin atmosphere behaves from hour to hour. Throughout each Martian day or sol, InSight detected gentle rises and falls in air pressure as the atmosphere warmed, expanded, and then contracted again after sunset. Its wind sensors tracked shifting breezes across the plains and recorded the passage of dust devils, revealing how these swirling vortices lift and redistribute fine surface dust. Perhaps most remarkable was InSight's seismometer, which proved sensitive enough to detect pressure waves generated by atmospheric turbulence. Passing dust devils left clear seismic signatures, effectively turning the lander into a combined weather station and ground motion detector. By linking atmospheric and seismic data, scientists gained unprecedented insight into Mars' daily weather rhythms, seasonal variations, and the intimate connection between the planet's surface and its fragile atmosphere, refining our understanding of how Mars remains active today. Mars experiences some of the most dramatic seasonal air pressure changes of any planet in the solar system. These fluctuations are driven primarily by carbon dioxide, which makes up more than 95% of the Martian atmosphere and behaves uniquely as the planet's seasons shift. During winter at one pole, temperatures fall so low that carbon dioxide freezes directly out of the air, forming a seasonal ice cap. As this gas condenses onto the surface, a significant portion of the atmosphere is temporarily removed, causing global air pressure to drop. At the same time, the opposite pole enters spring. Carbon dioxide ice that accumulated during the previous winter begins to sublimate, changing directly from solid back into gas, and returns to the atmosphere. This exchange restores atmospheric mass and raises pressure across the planet. Together, these opposing processes create a rhythmic, planet-wide breathing effect that repeats every Martian year. As pressure rises and falls, atmospheric circulation shifts, driving seasonal winds, influencing dust activity, and affecting the movement of trace water vapor. Landers and orbiters have measured these changes with remarkable precision, revealing pressure variations of more than 20% over a single year, an essential factor in understanding Mars' weather and climate today. Mars is constantly bombarded by high levels of radiation, far greater than anything experienced on Earth. This exposure comes from two major sources: energetic particles from the Sun, known as solar radiation, and cosmic rays, high-energy particles originating from outside our solar system. On Earth, we are shielded by a thick atmosphere and a strong global magnetic field that deflects and absorbs much of this harmful energy. But Mars has neither. Its atmosphere is less than 1% as dense as Earth's, and its once active magnetic field faded billions of years ago, leaving the planet's surface largely unprotected. Measurements from missions like Curiosity and MAVEN show that radiation on the Martian surface can fluctuate with seasons, dust storms, and solar activity. When the Sun erupts with powerful flares, the radiation intensity at Mars can increase dramatically. This harsh environment affects everything, from the preservation of ancient organic molecules in the soil to the safety of future astronauts. Understanding these radiation levels helps scientists determine how materials weather over time, how deep life would need to exist to survive, and what engineering challenges must be solved before humans can safely explore Mars. High above the Martian surface, thin water ice clouds drift swiftly across the sky, carried by winds far stronger than anything experienced at ground level. Though these clouds are delicate and often barely visible, they cast faint, fast-moving shadows that race silently across the terrain below. Rovers and orbiters have captured these fleeting scenes, revealing long, dark streaks sweeping over dunes, rocky plains, and canyon floors. Because Mars' atmosphere is extremely thin, these shadows appear softer and more diffuse than those on Earth, yet they can move with surprising speed as high-altitude winds shift direction. Their motion provides valuable clues about conditions far above the surface, where direct measurements are limited. In certain seasons, clouds form more readily above massive volcanoes and elevated plateaus, producing extended trains of shadows that stretch for kilometers. Time-lapse imagery shows these patterns flickering and reshaping as clouds evolve, dissipate, or reform within minutes. By studying cloud shadows, scientists gain insight into atmospheric layering, wind strength, humidity, and the subtle but dynamic processes that continue to shape Mars' weather today. Although Mars is a cold and arid planet, small but important amounts of water vapor still circulate through its atmosphere. This trace moisture is released mainly during warmer seasons, when sunlight heats surface ice near the poles and across some mid-latitude regions, causing it to sublimate directly into vapor. Unlike Earth, this process occurs without melting, as liquid water is unstable under Mars' thin atmospheric pressure. Once airborne, water vapor is transported by winds across the planet, rising to higher altitudes during the daytime and settling again as temperatures fall. As the atmosphere cools, this vapor can condense into extremely thin water ice clouds or return to the surface as frost, particularly during the cold Martian night. Over time, this continuous exchange redistributes moisture between the polar ice caps, the atmosphere, and the surface. Orbiters and landers have tracked these subtle movements with precision, revealing a seasonal water cycle driven not by rainfall, but by sublimation, condensation, and atmospheric transport. Understanding this cycle helps scientists trace how water behaves on Mars today and how it may have moved when the planet was warmer and wetter in the distant past. On Mars, even the calmest days are never completely clear. fine dust particles, some no larger than smoke grains, remain suspended in the thin atmosphere, softening the distant horizon into a pale, diffuse glow. This ever-present haze is one of the most recognizable features of the Martian sky. Because the atmosphere is too weak to settle dust quickly, these tiny particles can linger for days or even weeks, drifting slowly with gentle winds and subtly changing the color and brightness of the horizon. At sunrise and sunset, the effect becomes especially striking. Low-angle sunlight scatters through the suspended dust, creating soft gradients of gold, amber, and muted red that fade into a hazy bluish tint near the sun. Rovers have captured scenes where mountains and mesas appear ghost-like in the distance, their outlines blurred by the fine particles floating between them and the viewer. Studying this haze helps scientists understand how dust is transported across the planet, how it influences surface temperatures, and how even quiet atmospheric conditions contribute to the slow reshaping of Mars' environment. The horizon haze is a constant reminder that the Martian atmosphere, though thin, is always in motion. Mars is famous for its dust, composed of extremely fine, micron-sized grains formed largely from volcanic rock that has been broken down over billions of years by impacts, temperature changes, and wind erosion. These particles are so small and lightweight that even weak Martian winds can lift them from the surface and carry them into the planet's thin atmosphere. Once airborne, dust grains can remain suspended for long periods, drifting slowly across the planet under the influence of large-scale atmospheric circulation. Unlike sand on Earth, Martian dust behaves almost like smoke, spreading evenly and giving the sky its characteristic pale reddish hue. As this dust moves through the atmosphere, it absorbs and scatters sunlight, warming the air while slightly cooling the surface below. This exchange of energy plays a major role in controlling daily temperature swings and shaping regional weather patterns. Over time, dust gradually settles back onto the surface, coating rocks, dunes, landers, solar panels, and entire landscapes in a thin, uniform layer. Repeated cycles of lifting and settling constantly reshape the surface at a subtle scale. By studying how dust grains rise, travel, and resettle, scientists gain crucial insight into wind strength, surface conditions, and the delicate processes that drive Mars' dynamic climate system today. On Mars, dark volcanic sands play a powerful role in shaping how the atmosphere behaves close to the surface. These sands absorb sunlight far more efficiently than the surrounding bright dust and rock, causing them to warm rapidly during the daytime. As the darker ground heats up, it transfers energy to the thin air directly above it, making that air expand and rise in narrow, buoyant columns known as thermals. Even though Mars' atmosphere is less than 1% as dense as Earth's, these thermals can still form with surprising strength. As warm air rises, cooler air flows in to replace it, creating small but persistent pockets of turbulence near the ground. Rovers and orbiters have observed shimmering heat waves rising from dune fields, providing direct evidence of this vertical motion in the lower atmosphere. In some regions, thermals become strongest around midday when surface heating peaks. These rising air columns can help lift fine dust, seed small vortices, and contribute to the formation of dust devils. Over time, they also redistribute grains across dune slopes, subtly reshaping the landscape. By studying thermals over dark sands, scientists gain valuable insight into surface heating, boundary layer weather, and the delicate interactions between Mars' terrain and its thin, dynamic atmosphere. Each Martian winter, a powerful polar vortex forms high above the planet's poles, creating one of the most dramatic atmospheric systems on Mars. As temperatures plunge to extreme lows, carbon dioxide freezes out of the atmosphere and the polar region cools rapidly, causing dense, frigid air to sink and spiral. This rotation, driven by seasonal temperature imbalances and the planet's spin, traps cold air in a swirling, isolated pocket that can stretch hundreds of kilometers across. The vortex acts as a barrier, preventing warmer air from mixing into the polar night and locking in some of the coldest temperatures found anywhere on Mars. Orbiters observing in infrared light reveal the vortex as a rotating structure of chilled gases and thin clouds, shifting shape as it intensifies through the winter season. When spring sunlight returns, the vortex weakens and eventually breaks apart, releasing stored gases back into global circulation. These seasonal changes influence everything from wind patterns to dust movement and even the behavior of the planet's seasonal CO2 caps. Understanding the polar vortex helps scientists track atmospheric flow, model Martian weather, and compare Mars climate dynamics to similar systems on Earth and other planets. Mars' climate tells a story of loss. A planet that once held a thicker, warmer atmosphere now endures extremes of cold, radiation, and dust. Winds still move across its surface. Seasons still advance and retreat across its poles. But the air that once shielded Mars from space continues to escape, atom by atom, into the solar wind. By studying its weather and atmosphere, scientists trace how Mars transformed, from a world capable of sustaining rivers and lakes, to the cold, arid desert we observe today. Yet the story does not end in the sky. Beneath the surface and frozen into the landscape itself, evidence of water remains. In Part 3 we will explore Mars' water, ice, and ancient lakes, and what they reveal about the planet's most habitable past.